Hello and welcome to our first video of examples from section 10.4 of our calculus text. This section involves the alternating series test, trying to estimate the sum of a convergent alternating series, and also absolute and conditional convergence. This first video will look at a few examples, looking at where the alternating series test applies, when it doesn't, what conclusions that we can draw. So let's start off by stating the alternating series test. We're going to let B sub n be a positive and decreasing sequence of numbers. Then we're going to look in that case at the limit as n goes to infinity of B sub n, and if that limit is 0, then the series summation n equals 1 to infinity minus 1 to the n plus 1 B sub n, that series is going to be a convergent series. So this is one time where the limit of the general term being 0 actually allows us to conclude that the series converges. Ordinarily that's not the case, but in the case of an alternating series, if the general term is heading towards 0 and the sequence of positive numbers is decreasing, then you've got a convergent series. So let's look at a couple of examples here. Our first one is summation n equals 1 to infinity minus 1 to the n plus 1, 1 over n cubed. So in this case, B sub n is 1 over n cubed. Definitely positive. And we want to ask, is it decreasing? Well, here's one way we can tell. Is a sub n plus 1 less than a sub n? Well, is this true? Well, I can expand this denominator of the expression on the left. And so I want to ask, is 1 over n cubed plus 3n squared plus 3n plus 1 less than 1 over n cubed? Most definitely. We're adding something positive to this denominator over here, which makes the fraction smaller. So yes, so it's positive, it's decreasing, and so then I want to look at the limit as n goes to infinity of B sub n, 1 over n cubed. Well, as n gets big, n cubed gets really big, and so I get a bigger and bigger denominator. And so that limit is 0. So by the AST, summation n equals 1 to infinity minus 1 to the n plus 1, 1 over n cubed, converges. Our next example is an alternating p-series, negative 1 to the n plus 1, 1 over the square root of n. Our previous example was also an alternating p-series with p equal to 3. So here's b sub n equaling 1 over the square root of n. Definitely positive when n is positive. And then decreasing, well, is a sub n plus 1 less than a sub n? Yes, it is. Again, n plus 1 is bigger than n, so the square root of n plus 1 is going to be bigger than the square root of n. And so therefore I've got a bigger denominator over here, which means I've got a smaller fraction. So again, we look at the limit as n goes to infinity, b sub n. As n gets big, the square root of n gets big. This is going to 0. So by the alternating series test, summation n equals 1 to infinity minus 1 to the n plus 1, 1 over the square root of n, converges. So it's a pretty easy test to apply if you can demonstrate the decreasing part and show that the limit is equal to 0. But let's talk about a case where the alternating series test doesn't actually apply. Here, b sub n is 2k plus 1 over 3k minus 1. Now, I could go through the steps to show you that b sub n is a decreasing sequence, but I'm going to step over that and take a look at the limit as n goes to infinity of b sub n. Okay, this time I've got polynomial over polynomial. The degree of the numerator is equal to the degree of the denominator, and so we know that this limit is going to be 2/3. Now, one thing I can say about 2/3 is 2/3 is definitely not 0. And so the assumption of the alternating series test doesn't apply. So we can't draw any conclusion from the alternating series test. But what we can do is we can go back and think about the nth term divergence test. That said that if the limit of the general term was not equal to 0, then the series diverges. And so what we have here is limit as n goes to infinity of 2n plus 1. These should be n's up here. My apologies. These should be n's. So this limit as n goes to infinity is 2/3, which tells me that if I take the alternating sequence, that does not exist. So this goes back to something that we talked about in section 1 of this chapter, that alternating sequences whose positive term doesn't go to 0 means that the alternating series is oscillating back and forth. In this case, as n gets bigger and bigger, my terms are oscillating back and forth between negative 2/3 and positive 2/3. The limit doesn't exist. And so by the nth term divergence test, the series diverges. So the bottom line with the alternating series test is we can never draw a conclusion. So we can never conclude divergence by the AST. If you go back and look at the statement for the alternating series test, that the only conclusion that you're allowed to draw from it is convergence. So if the limit of b sub n is equal to 0, then the alternating series converges. But if the limit of b sub n is not equal to 0, then the limit of minus 1 to the n plus 1 b sub n doesn't exist, and so therefore the nth term divergence test kicks in. And so we're generally speaking going to be either concluding convergence by the alternating series test or divergence by the nth term divergence test when it comes to alternating series.